Welcome to the Nordic Venture Show, your speed date with the coolest ventures, brightest founders, and exciting things happening in the Nordics. In this episode, our venture date is with Arctic Instruments, a deep tech spin-off from VTT Technical Research Centre of Finland, pioneering quantum readout solutions.
Okay, let's unpack this. When we talk about the incredible potential of quantum computers, tackling problems currently impossible, fundamentally changing industries, it's easy to get swept up in the big picture. But making that potential real involves solving some truly mind-bending engineering challenges. At the absolute rock bottom, think about this. How do you actually know what a super-sensitive quantum bit, a qubit, is doing? It's like trying to hear a whisper in a room colder and quieter than anything you can imagine without making a sound yourself.
Right. It's incredibly delicate.
So this deep dive is all about a critical piece of that puzzle, the technology needed to accurately listen to those incredibly delicate quantum signals from a qubit. We're exploring the work of a company focused precisely on this.
Exactly. And the fundamental hurdle is translating that fragile quantum state, is the qubit a 0, a 1, or maybe some combination, into a clear, usable classical signal, something we can actually measure with our normal electronics.
And this needs to happen right there.
Right there. Incredibly sensitive, low noise amplification happening literally centimeters away from the qubits in their super cold millikelvin environment. Getting that first signal out reliably, accurately, it's one of the biggest bottlenecks in building larger, more powerful quantum computers. Seriously.
How sensitive are these qubits, really? What kind of energy scales are we actually dealing with here?
Oh, they're extraordinarily sensitive. The energy difference between a superconducting qubit 0 and 1 state is minuscule, tiny. To put it in perspective, it's typically less than 1,000th of the kinetic energy of just one air molecule in the room with you right now.
Wow. Okay.
So you have to probe them with electrical signals so faint they barely register, precisely to avoid disturbing that delicate quantum state you're trying to measure.
Your measurement shouldn't change the outcome.
Exactly. It shouldn't change what the qubit is doing. Now, those weak signals, they need significant amplification to be detected by, classical systems. But any amplifier naturally adds noise.
The unavoidable part.
Physics puts a fundamental limit on how little noise you can add, sometimes called the standard quantum limit. In this context, it's about half a photon's worth of noise energy.
Half a photon, that's basically nothing.
It's incredibly small. And adding more noise than that obscures the signal. The first amplifier in the chain is absolutely critical.
Why the first one specifically?
Because its added noise sets the signal-to-noise ratio for everything that follows. If that first step is noisy, you lose the qubit state information right there. Oof.
Okay, so that really sets the stage for why this is such a hard problem. Now, we're looking at a company that's spun out of a leading research center, right? With deep roots in superconducting circuits, specifically tackling this. What's their approach?
Yeah, exactly. They came out of a place with decades of experience.
And this company was formed with a pretty clear mission, it seems, to simplify the deployment of this crucial low-noise readout tech. Essentially, they aim to take a major technical headache away from quantum computer builders.
That's the idea. Let the builders focus on other complex parts of their systems, like the qubits themselves or the control logic. Their flagship product is a specific type of amplifier called a traveling wave parametric amplifier, or TWPA for short.
TWPA.
It's designed and optimized specifically for this high-fidelity qubit readout, and it operates in a frequency range called C-band, which is typically between 4 and 8 gigahertz.
Why that range?
That's important because it's the frequency range where many superconducting qubits are designed to resonate and operate. You need your amplifier to listen where the qubits are talking.
All right, let's dig into the technical side of this amplifier then.
Yeah.
What are its standout features? What makes it special?
Well, the first thing that jumps out is the noise performance. They consistently measure their added noise to be below 1 photon.
Below 1 photon. And the limit is half a photon.
The theoretical quantum limit, set by the uncertainty principle itself, it's a fundamental barrier. So being routinely measured below 1 photon is incredibly close to that theoretical minimum. That's really, really good.
Okay, that's impressive. What else? They also emphasize impressive bandwidth and dynamic range. We're talking typical values of over 2 gigahertz instantaneous bandwidth.
Which is huge.
And a dynamic range of 90 decagram. Can you unpack why those numbers matter?
Sure. The high bandwidth over 2 gigahertz means this single amplifier can listen to signals from many qubits operating at slightly different frequencies simultaneously.
Splicing.
Exactly, crucial for scaling. Instead of one wire per qubit, you can handle many on one line. And that dynamic range, 9 and 90 DDM, that's an incredibly faint signal level it can handle as input.
The qubit whisper.
Right. It means the amplifier can handle that whisper quiet input from the qubit while also managing the much stronger pump signal it uses internally for amplification, without getting overwhelmed or, crucially, distorting that delicate qubit signal.
You mentioned a pump signal.
Yeah. Parametrically amplified signals need a pump. Technically, their amplifier uses something called three-wave mixing for its operation.
Okay, three-wave mixing. Is that different from other approaches?
It is different from, say, four-wave mixing, which is used in some other amplifiers. And there are real advantages to three-wave mixing here. For instance, the pump frequency, that's the powerful signal providing the energy for amplification, can be placed far above the actual signal frequency where the qubit information is.
And why is that good?
It makes it much easier to filter out that strong pump signal later so it doesn't leak back and potentially mess with the very sensitive qubit.
Protection.
Right. It also helps increase the dynamic range by avoiding certain nonlinear effects that can happen when signals are too close together. And another thing, you can tune its performance in situ.
Meaning while it's cold, in the fridge.
Exactly. While it's cold and operating, you can adjust its operation using the pump power and frequency and also something called a magnetic flux bias. This gives you flexibility for different system designs and fine-tuning.
Okay, that flexibility sounds useful. Now, there are also some really clever practical advantages, right? Like how they handle that flux bias you mentioned.
Yes, this is quite neat.
Instead of needing external coils to create that magnetic field, which take up space and generate problematic stray magnetic fields in a dense, cold environment.
Which is a real headache when you're packing things tightly.
They've patented an integrated flux line right there on the chip itself.
Mm-hmm.
This generates the necessary magnetic field precisely where it's needed with minimal stray fields. That's key for packing many components closely together as you scale up.
Absolutely. Minimizing crosstalk and interference is huge.
And speaking of packing, size is critical in those dilution refrigerators. They get very crowded.
Well, yeah, space is at a premium. Every cubic millimeter counts.
They have a really small form factor, just 22 by 18 by 15 millimeters. Tiny.
That is very compact for this kind of device.
So a compact amplifier means you have more valuable room for, well, more qubits and all the other necessary plumbing and wiring down there.
Definitely saves space.
Reliability is another big point they make. They use niobium-based Josephson junctions in their design.
And niobium is a well-understood material in superconducting circuits.
Right. The benefit here, they say, is that these components show no aging effects.
Yeah.
Once the amplifier is installed and tuned up, its parameters remain constant, indefinitely.
So no drift over time.
Apparently not. No need for regular retuning, which I imagine saves a huge amount of time and complexity in operating large quantum systems. You tune it once, and it stays put.
That's a massive operational advantage, if true. Calibration is a big overhead, and they've really put effort into their manufacturing, it seems. They emphasize that their process is mature and scalable.
So not just lab curiosities.
Right. They aren't just building these one-off prototypes in a research lab. They claim they're capable of producing and testing these sophisticated, near-quantum limited components in volume now.
In volume, that's significant.
Yes, and they can even tailor the specific operating point, the exact frequency range, gain, etc., of individual amplifiers for specific customer needs through automated testing. That ability to produce volume with consistency is a major factor for anyone trying to actually build and scale quantum computers. You need reliable parts, and lots of them.
Okay, so let's connect this back to the big picture. Why is this specific component, this amplifier, so crucial for the future of quantum computing?
Well, think about where quantum computing is heading, or where we hope it's heading.
Today's systems might have, around 100 qubits, maybe using 10 or 20 of these types of amplifiers for readout, give or take?
Something like that, yeah. But to unlock the truly revolutionary potential drug discovery, material science, complex optimization.
The big promises.
The big promises. We need to scale to thousands, maybe tens of thousands of qubits. Maybe more eventually.
And that's the bottleneck this company is addressing head on, isn't it?
Precisely. A quantum computer with, say, 10,000 qubits is going to need thousands of these incredibly sensitive low-noise amplifiers.
One or maybe slightly fewer per qubit, depending on multiplexing.
Right. But thousands overall. And crucially, they all have to perform consistently, operating reliably near that quantum limit, day in and day out. The ability to supply that kind of volume with that level of performance and consistency is something this company believes they can do uniquely well right now. That's their claim.
And the potential impact of successfully scaling quantum computing. It's enormous, isn't it? Industries like chemicals, life sciences, finance, mobility, they could all be transformed.
That's the hope. Some projections put the potential economic value into the trillions of dollars by a year like 2035.
Trillions.
Huge numbers. But none of that happens without solving the hardware challenges. And scaling up these high-performance readout components is absolutely essential. It's a foundational piece.
Let's look at the team behind this. It's not just the tech, it's the people too.
Absolutely. It seems to be founded by seasoned scientists. The CEO, for example, has 15 years of research and managerial experience, focused specifically on superconducting circuits and parametric amplifiers.
He had experience from world-leading institutions too.
Right. Deep background in the field.
And the CTO.
Yeah.
Described as the lead designer, someone with a 15-year scientific career at that research center we mentioned.
Holds multiple patents in the field, apparently.
The mastermind behind the complex circuit design and the tricky cryogenic testing, it sounds like.
Yeah, the technical core. And the COO brings a multidisciplinary background experience in high-volume semiconductor manufacturing, emerging tech.
So handling the production side.
Leading the crucial fabrication process, yeah. Making sure they can actually build these things reliably and scale up.
So this company isn't just some random startup with a bright idea. It's framed as a direct outcome of decades of significant investment and deep expertise built up in superconducting and quantum technologies at that research center.
It's like taking cutting-edge long-term research results and finally turning them into commercial products that people can buy and use now.
Commercializing the science.
Exactly. And the perspectives we've seen seem to reinforce this picture. The CEO talks about reaching a level of maturity in their fabrication and testing volume that they see as a real advantage. He acknowledges scaling quantum computers is still challenging, but argues the need for high-quality, scalable components like theirs is undeniable.
And funding helps speed things up.
Right. He mentioned that recent funding allows them to really accelerate the development efforts, push harder, faster.
We also heard from a funding partner who highlighted the team's deep competence and noted that this product solves one of the most critical challenges today.
Yeah, they specifically pointed out how difficult it is to build a component that is both accurate, reliable, and actually available for use right now, not just a lab result.
Availability is key.
And someone from the original research center echoed this, emphasizing their goal of seeing research results commercialized and scaled. They see this company as a prime example of taking top-tier fundamental research and scaling it into a global business.
Okay, let's maybe get a slightly simpler picture of how this technology actually works. How does it tell us a qubit's state?
Right, the basic mechanism. It relies on a widely used technique called dispersive readout.
Dispersive readout.
Okay, the core idea is quite clever. The state of the qubit, whether it's a 0 or a 1, subtly changes the properties of something it's coupled to, usually a readout resonator.
Like a tiny tuning fork.
Sort of, yeah. Think of the resonator like a tiny, super-sensitive radio receiver or filter tuned to a specific frequency. You send a weak probe signal at that frequency towards it.
Okay.
Now, if the qubit is in its ground state, let's call that 0, its interaction with the resonator means the resonator acts like a strong filter right at that specific probe frequency. So the probe signal largely reflects back. It bounces off.
Bounces back. And if the qubit is a 1?
If the qubit is in its excited state, the 1 state, it slightly shifts the resonator's properties. It's like it slightly detunes that filter frequency. So now the probe signal is no longer exactly at the resonator's peak filter frequency. Instead of reflecting, it passes through the resonator.
Reflected means 0, transmitted means 1. Roughly.
That's the core idea. Reflected or transmitted tells you the state. But you need other components too. Isolators, for example.
What do?
They act like one-way valves for microwave signals. They protect the sensitive qubit from any noise coming back up the line from the amplifier, and they help route the reflected or transmitted signal towards the amplifier, not back towards the probe source.
Got it. One-way street.
And you usually need a diplexer too. That separates the very low-power probe signal going in from the much higher frequency, high-power pump signal that the amplifier needs. Keeps them from interfering.
Okay, so the probe signal, carrying that reflected transmitted information, reaches the amplifier. How does the amplification happen near the quantum limit?
Right. Inside the amplifier, that TWPA, the probe signal and the pump signal travel together through a specific nonlinear circuit structure.
Nonlinear.
Meaning its response isn't directly proportional to the input. It often involves a long, meandering transmission line embedded with thousands of Josephson junctions.
Those superconducting components again.
Yes. These junctions provide the crucial low-loss nonlinearity. This allows energy from the high-power pump tone to be efficiently transferred to the tiny probe signal, amplifying it significantly while ideally adding the minimum possible noise, getting very close to that quantum limit we discussed.
And the flux bias helps tune this.
Exactly. That integrated flux line allows fine-tuning of how these junctions behave, and thus the amplifier's characteristics, its gain, frequency response, and so on.
Okay, so the amplified signal comes out. Then what?
After the amplifier, the now amplified signal, which is a much stronger version of that original reflected or transmitted wave carrying the qubit state info, emerges. It's still mixed with the powerful pump signal, though.
I need to get rid of that.
Right. So filters then remove the high-power pump signal. It's done its job and could saturate the electronics downstream. The amplified qubit signal then leaves the super cold environment, travels up the wires,
Back to room temperature.
back towards room temperature, where it's processed by standard classical electronics, digitizers, FPGAs, computers. By averaging the signal over a short time, typically tens to hundreds of nanoseconds, the signal-to-noise ratio gets high enough that you can confidently distinguish between the reflected signal level and the transmitted signal level.
And that tells you the state.
That tells you definitively if the qubit was measured in its ground state or its excited state. You've successfully read its state.
And one of the most practical benefits, linking directly back to scaling, you mentioned it before, is frequency multiplexing.
Yes, absolutely key.
Because this amplifier has such wide bandwidth and high dynamic range,
That 2+ gigahertz we talked about.
you can actually read out the states of multiple qubits simultaneously on the same physical line coming out of the fridge.
Exactly. Each qubit gets its own readout resonator, each tuned to a slightly different frequency within that amplifier's bandwidth.
Like different radio stations.
Precisely. The wideband amplifier can handle all these different frequency channels, all these stations, at once. This dramatically reduces the number of expensive, heat-leaking cables and components needed as you scale up. It makes the whole system much more efficient and manageable.
That makes sense. Fewer wires, less complexity. Now, looking at recent developments, the company seems to be gaining momentum. They secured significant funding, didn't they?
Yeah, EUR 2.35 million in a year, like 2024, led by an early-stage VC firm known for backing potential market leaders. Shows confidence.
And they're active in the community.
It seems so. We saw mentions of them participating in international physics summits and delegations in a year like 2025, getting their name out, engaging with researchers and potential customers globally.
And it's interesting timing too, right? Around the same time, in 2024, there were announcements about record-breaking superconducting qubit coherence times.
Yeah, progress in the underlying qubit tech itself, which is good news for them because better qubits still need better readout. The whole ecosystem needs to advance together.
So bringing this all back to you, the listener, who's interested in where technology is heading, this deep dive really shows that unlocking the amazing potential of quantum computing isn't just about creating those delicate qubits themselves. That's hard enough. But it's fundamentally about mastering the incredibly complex engineering challenges of the support systems, like accurately, reliably, and efficiently reading out the state of those qubits when they're operating near absolute zero.
It's easy to forget those parts. But companies that focus on solving these specific, often hidden, but absolutely critical bottlenecks, they are essential for enabling the entire field to move.
Building the infrastructure.
They really are. They're doing the foundational engineering work that paves the way for building the much larger, more powerful quantum computers that could one day tackle problems currently way beyond our reach. So I think the core takeaway here is pretty clear. High-quality, scalable amplification technology operating close to the quantum limit is just a fundamental requirement for the future of quantum computing. And companies dedicated to mastering this specific challenge are playing a vital, truly enabling role in making that future a reality.
Which leaves you with this thought to chew on. As you look at seemingly futuristic technologies like quantum computing, consider how many other hidden, highly technical components and specialized pieces of expertise are required behind the scenes. Things needed just to make them work, and crucially, to create them reliably at scale. What other picks and shovels companies like the one we discussed today are quietly enabling the next wave of technological advancement that we rarely even hear about?
Thanks for tuning in. You can follow us on Spotify, Apple Podcasts, Google Music, or your favorite app. And connect with us on LinkedIn for more stories and insights.